you very much. Thanks for the introduction and thanks for the invitation. I'm basically filling in for Professor Detlef Dürr, which is my longtime teacher and PhD supervisor. And he was scheduled to talk, but he was advised against a long flight for medical reasons, so nothing serious, but he couldn't come. And so I'm very honored to step in, and I'm very grateful to the organizers for inviting me and let me give this talk. So as I said, I'm a longtime student of Detlef Dürr's, and they are also writing together right now a textbook on quantum mechanics. So I think I can tell you pretty much what he would have told you. I'm not sure if I can tell it as good as he would have told you, but I will do my best in any case. So I guess the title of our meeting, Fundamental Problems in Quantum Mechanics, allows for an optimistic reading and a pessimistic reading. So the optimistic reading would be, we know quantum mechanics, we understand it very well, it works extremely well. Let's see what are the real interesting open problems to address. There's also a pessimistic reading, I guess, which would be, what are the fundamental problems of quantum mechanics? So to speak, what is wrong with quantum mechanics? And some of you, your initial reaction may be there's nothing fundamentally wrong with quantum mechanics, but that depends on what you mean by quantum mechanics, and also that depends on what you expect from a physical theory. In some sense, when we're talking about standard textbook quantum mechanics, there's indeed something fundamentally wrong with this theory. And the best way to see that there's something fundamentally wrong with this theory is to talk about the famous measurement problem. So what is the measurement problem? So most simply put, the measurement problem is that standard textbook quantum mechanics involves just one equation, the Schrodinger equation, describing the time evolution of a wave function or a quantum state. And this equation in and by itself does not describe the phenomena. This is relatively easy to see, for instance, like this. So let's suppose we consider a quantum system in some state phi I. So phi I could range over a finite set or an infinite set, or just about between 1 and 2, if you think, for instance, about a spin measurement. So if you want to think about phi 1 as a state z spin up and phi 2 as a spin state z spin down. And now we want to do a measurement on this quantum system, and we couple a measurement apparatus. And of course, this measurement apparatus, if we take quantum mechanics seriously, must also be described by quantum mechanics. That is, its state must also be described by a wave function. Let's call this wave function of the ready state capital phi 0, right? So the founding fathers, at least some of them of quantum mechanics, they denied that something as big as a measurement apparatus has a wave function. But of course, we understand a macroscopic system like a measurement apparatus also as made out of atoms or molecules. And these atoms are made up of nucleons and electrons and so on. And if they all have a wave function and are described quantum mechanically, then of course the macroscopic system, the measurement apparatus, also has to be describable in terms of quantum mechanics, as at least in principle, even if that description may be too difficult to give in practice. So let's assume that the measurement procedure is such that the microscopic system couples to the macroscopic system. And if the microscopic system is in the state phi 1, we get the measurement result indicated by corresponding to the quantum state of the apparatus, which is capital phi 1. This could be, for instance, a detector clicking, or just a pointer pointing to the left. And if the microscopic system is in the state small phi 2, then again, the microscopic system couples to the measurement apparatus, and they evolve under the Schrodinger evolution, and then the measurement apparatus shows the result too, for instance, by a pointer pointing to the right. However, since the Schrodinger equation is a linear equation, a linear wave equation, we can consider for the microscopic system, the superposition of the states phi1 and phi2. So I'm leaving here out the normalization constant. Of course, we would have to normalize that. But the critical point is the microscopic system could be in a superposition of state 1 and state 2. For instance, in a superposition of Z spin up and Z spin down. And then, if we couple that to the measurement apparatus, we get an unreal result. We get a macroscopic superposition of a pointer pointing to the left and a pointer pointing to the right. Needless to say that this is an irrealistic result. This is nothing that we ever observe, and it's not even clear how such a state would look like. That, in short, is the famous measurement problem of quantum mechanics. And of course, this is nothing else than Schrödinger's cat problem. If you remember the Schrödinger cat experiment, right, then phi1 would be an atom that has not yet decayed. Phi2 would correspond to the state of an atom that has decayed, then has set in place this mechanism that Schrödinger describes, which destroys a little glass of poison that poisons the cat, and that would evolve into a state of a dead cat, whereas the first state would evolve into a state of an alive cat. And Schrödinger's cat problem is, of course, that this microscopic superposition, this initial microscopic superposition, under the linear time evolution, evolves into a macroscopic superposition of the dead cat and the alive cat. Right? So you've probably heard a million times about Schrödinger's cat problem, so maybe this seems very basic to you, but you don't have to be embarrassed if you've never really thought deeply about Schrödinger's cat. I think that most people, most practicing physicists, have never really thought very deeply about Schrödinger's cat problem because it is somewhat, I don't know, it feels somewhat like popular science nowadays, right? If you watch an episode of The Big Bang Theory, they might make a joke about Schrödinger's cat or whatever. So it doesn't really feel like something that concerns you when you want to do physics. But it should concern you because it is a deep problem, and we owe it to Schrödinger to make this very clear with this somehow funny and radical but very illustrative picture. And here is what Schrödinger himself wrote about that. It's also interesting that very few people actually look at what Schrödinger said about that. So he said, it is typical of these cases that an indeterminacy originally restricted to the atomic domain becomes transformed into macroscopic indeterminacy, which can then be decided by direct observation. Right? So of course we see if the measurement apparatus, if the pointer points to the left or if the pointer points to the right. Right? But if we have just a Schrödinger evolution, a microscopic superposition would evolve into a macroscopic superposition, what he calls macroscopic indeterminacy. That prevents us, he goes on, from so naively accepting as valid a blurred model for representing reality. In itself, it would not embody anything unclear or contradictory. There is a difference between a shaky or out-of-focus photograph and a snapshot of clouds and fog banks. Okay, and the last sentence is somewhat cryptic. It's very nicely written, but somewhat cryptic. But this is crucial. Okay, many people present Schrödinger's cat paradox as something just to show how crazy, how counterintuitive quantum mechanics is. But that this is somehow what we learned that nature is really like. But Schrödinger, of course, wanted to make exactly the opposite point, that nature cannot be like that the quantum mechanical description that leads to such a macroscopic superposition of dead cat and alive cat, or of a pointer pointing to the left and a pointer pointing to the right, cannot be correct or it cannot be complete. Right? There's a difference between a shaky or out-of-focus photograph, right? A description, a presentation of nature which is somehow incomplete, and a snapshot of clouds and fog banks, right? Or something which is actually unsharp and incomplete and indeterminate. Right? So his point was that this quantum mechanical description given by his wave function cannot be the whole story. It is an indeterminate description of something which cannot itself be indeterminate, because the measurement apparatus points either to the left or to the right, and the cat is either dead or alive. That was his point. So let's put the measurement problem more precisely, and I think the most precise formulation of the measurement problem can be actually found in the philosophical literature. There's a great philosopher of science, Tim Maudlin, which wrote an important paper. It's actually called Three Measurement Problems. But the main formulation of the measurement problem, which is what we discussed, is put here. That there are three claims that I guess most people, most physicists would endorse about quantum mechanics, and these three claims are just logically inconsistent. Okay, you cannot believe in these three things at the same time. This leads to a logical contradiction. The first statement or principle is that the wave function of a system is a complete description of that system. So the wave function of a system is complete, meaning that the wave function and the wave function alone, or the quantum state, if you prefer this terminology, specifies all the physical properties of the system. The second principle is that the wave function always evolves in accord with a linear wave equation. For instance, the Schrodinger equation. But of course, this point is not limited to the Schrodinger equation and the non-relativistic regime, but you have the same problem in relativistic quantum mechanics and in quantum field theory. So it could be the Klein-Gordon equation or the Dirac equation or whatever unitary time evolution you have for the quantum state. Yes? Yes. 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 Right. Well, the problem is that this is an inconsistent or at least imprecise picture to make a split between a quantum world, the microscopic world that is described by quantum mechanics, and some macroscopic world that is not described by quantum mechanics. So first off, this is also sometimes called the Heisenberg split. And in standard Copenhagen quantum mechanics, what you said was part of the response to this measurement problem, that we are supposed to apply quantum mechanics just to microscopic system, and we are supposed to describe the measurement apparatus or macroscopic system in terms of classical mechanics. But I don't know if anyone still seriously believes in that, just for the reason that we understand that the measurement apparatus is also made up of microscopic particles, molecules of atoms and so on. And if the molecules and atoms that made up the measurement apparatus are described in terms of quantum mechanics, then in principle at least, the measurement apparatus itself is also describable in terms of quantum mechanics. And the second problem is that there is just no, so Bell called it the shifty split. There is just no precise way to make a split between the microscopic regime in which quantum mechanics is supposed to hold and the macroscopic world in which quantum mechanics is no longer supposed to hold. There's just no way making the split precise. And the third reason is that just in practice, increasingly, we want to apply quantum mechanics to larger and larger systems, to macroscopic systems, even to the universe as a whole in quantum cosmology. So nowadays, it's basically, most people agree that quantum mechanics, or the more fundamental theory of which quantum mechanics is the non-relativistic limit, must apply in some sense on all scales. Yes, please. Yes. Yes, please. Yes. these arise. I think we'll come to that. So, yeah, yes. Yeah, if you have follow-up, go ahead. So in this picture, there's no collapse yet. In this picture, this is just a Schrodinger evolution, which leads to a unitary evolution. And this unitary evolution leads to this macroscopic superposition of the pointer pointing to the left and the pointer pointing to the right. Although we, of course, observe only one of these possibilities. And now we will talk about the collapse, but the collapse here, if you look at these three statements, if you introduce a collapse, at least on a fundamental level, you are denying statement 2, right? Statement 2 is that the wave function evolves always in accord with a linear dynamical equation. And the collapse postulate, or a collapse models, we will also talk about a bit about precise collapse theories, which introduce the collapse not ad hoc, but as a physical law. They deny the second possibility. But the collapse somehow says that when the collapse occurs, the Schrodinger evolution is no longer valid. Yes? Mm-hmm. Is this a question or a comment? If I understand you correctly, then I would agree. Yes. Yes. No. Yes, this is of course a bit schematically. So I'm leaving out basically everything what this arrow does. This arrow is just the Schrodinger time evolution, and in the course of the Schrodinger time evolution, as soon as you have interaction between the small system and the measurement apparatus, you will have some form of you won't have this product form necessarily, but just so to speak, it doesn't really matter for the argument the details of these interactions. It just matters that somehow the measurement apparatus and the microscopic system can interact in such a way that if the microscopic system is in the state small phi 1, then the pointer will point to the left. And if the microscopic system is in the state phi 2, the pointer will point to the right. And then just by linearity, it comes out that if you take the superposition of the microscopic states, then you would have to end up in a superposition of the measurement apparatus, which is just an unreal result. Yes? Yes, so a description of a system, so one necessary condition for this completeness is if that two systems differ in at least one observable quantity, right? They must differ in their state description. This is not a sufficient condition, but it's at least a necessary condition, right? If a state description is complete, it must mean at least that if two systems differ in some observable way, in some observable quantity, then the state description must differ as well. Okay, and if you have, in the end, if we agree that in the end the state description of the system plus apparatus is this, right? It cannot be the case if the state description is complete, that one and the same state once describes a pointer that points to the left and once describes a pointer that points to the right. Okay, so we can, otherwise the state description cannot be complete. Right? Yes? Yes? Yes. So we will come to that too if you entangle the observer as well, which is just a consequential move. If you want to have to stay just with the wave function and the linear Schrodinger evolution, then you get a many worlds theory, then you get a many worlds picture. And this is not logically inconsistent. This is why the third statement is here. I didn't really come to read it, right? But the first statement is that measurements of, for instance, spin of a system usually, or at least sometimes, have determinate outcomes. That is, in the end of the measurement, the measuring device is either in a state which indicates spin up, or either the measurement apparatus, the pointer points to the left, or spin down. That is, in our schematic case, the pointer points to the right. And one logical possibility to solve the measurement problem is to deny this third statement and to say, no, in the end, indeed, what there is in the world is a pointer pointing to the left and a pointer pointing to the right. And we will go into more details about this possibility, but this leads to a so-called many worlds theory, to a so-called many worlds description. So in this case, you not only have a pointer pointing to the left and a pointer pointing to the right, you have an experimentalist seeing a pointer pointing to the left and an experimentalist seeing a pointer pointing to the right, and so on and so forth. So basically the whole universe is splitting or branching in this picture. But this is a logical possibility, yes. No, I don't think there is such an assumption. But if you take more and more of the environment into account, then just this as we just discussed and briefly with respect to the many worlds picture, this superposition will just include more and more of the environment. So it will include one experimentalist seeing the pointer pointing to the left and writing in his notebook that the pointer pointed to the left, and writing a paper about the pointer pointing to the left, and another experimentalist which sees the pointer pointing to the right and writing in his notebook that the pointer pointed to the right, and so on and so forth. So, yes. Yes. What is the point exactly? Yes. Well, so at least how I formulated this problem, or how this problem is formulated, at least it assumes that you can do some sort of experiment on the microscopic system. I mean, that you can do an experiment, for instance, a spin measurement, in which the outcome is either spin up or spin down. and which depends on the state of the microscopic system, some sort that you measure. And I think this should be uncontroversial. I mean, this is of course this scheme here is an idealization, of course, but I mean, you should. The point is very general, right? We know that there are microscopic superpositions of sorts, and we know that, at least in principle, if you have situations in which a macroscopic system somehow couples to the microscopic system and involves into one of two discernible macroscopic states, or one of several discernible macroscopic states, being a dead cat or an alive cat, or being be it a pointer pointing to the left or pointer pointing to the right, or I don't know, be it a light bulb being on or off, right? So if you have just a linear time evolution, that's a very general point, the microscopic superpositions will evolve into macroscopic superpositions. Yes. Yes. Right. Yes. Yes. Yes, maybe. Yes, maybe I should go on. Yes. So then we will see that. But I mean, there are some solutions and there are some things which are not solutions. So one observation, which is very important, but does not solve the measurement problem, okay, is decoherence. Decoherence means that these macroscopic wave functions, of course, they do not overlap in configuration space. Or in other words, in Hilbert space, they are orthogonal. Or in other words, if you would write down the density matrix, then the off-diagonal terms would be approximately 0. But this is not the point, right? This is also not the point of Schrödinger's cat experiment, or Schrödinger's cat Gedankenexperiment. Schrödinger was well aware of the fact that the wave function of a dead cat and the wave function of an alive cat, that they are decohered, right? That they do not superimpose. But this was not his point, right? His concern was not that the wave function of a dead cat and the wave function of an alive cat somehow overlap, which they do not. But his point was that the wave function of a dead cat and the wave function of an alive cat, they were just equally real if all you have is the wave function, right? So decoherence, as you can see also from the fact that decoherence doesn't deny either one of these propositions, okay? So decoherence doesn't add anything to the wave function. Decoherence doesn't change the linear Schrödinger evolution, right? This is the whole point, that you just get decoherence from the linear Schrödinger evolution. And usually decoherence, except if you combine it with a many worlds picture, doesn't want to deny that in the end you see just one of the possible results. You see either the pointer pointing to the left or the pointer pointing to the right. So decoherence is extremely important, and it will come up several times when we discuss the possible solutions to this measurement problem, but decoherence alone does not solve the measurement problem. Yes? Yes. There's only a very limited sense in which it matters if this system is closed or not. Okay, the whole point is that you have microscopic superpositions, and under the linear time evolution, you they evolve into macroscopic superpositions, and the larger you make your systems, the larger this branching becomes. And ultimately, if you take, I mean, the largest possible system is the universe as a whole, then basically the universe as a whole will evolve into a microscopic superposition. So in the many worlds community, you would say a branching universe. So one branch in which you measured spin up, and one branch in which you measured spin down, and these branches, they are decoherent, so they are causally disjunct from each other. They do not interact with each other anymore. But if everything you have is the state description given by the quantum state, by the wave function, then this is basically symmetric between these two possibilities. So both branches of the wave function, to the degree that the wave function describes the real state of the system, both these states are real, equally real. Okay, but it's good. Thanks for your question. It's good. So keep it up. If you have questions, let's just discuss about them. But so, yeah, now we have set up the measurement problem as the logical inconsistency of these three propositions. And now let's solve the measurement problem, or let's look at the possible solutions of the measurement problem, right? And if the, yes. So let's consider another non-solution, which I think is a non-solution. So the classical answer to that, basically from the old Copenhagen quantum mechanics, is to add one postulate to the formulation of quantum mechanics, which is the collapse postulate. So the collapse postulate is that whenever a measurement or an observation occurs on a microscopic system, the Schrodinger evolution is suspended. So basically the laws of nature don't hold anymore, and the wave function collapses into one of the possible eigenstates of the associated observable with probabilities given by Born's rule, basically. So, right, so you have a perfectly deterministic law. The Schrodinger equation is a deterministic equation, and quantum randomness usually only comes in with this collapse postulate, which suspends the linear Schrodinger equation and just says that basically in form of a deus ex machina, the observer or the measurement, whatever this is, suspends the Schrodinger evolution and collapses the wave function into one of the possible states. And I guess this is still how quantum mechanics is presented in most textbooks, but I mean, this is just nonsense for many different reasons, okay? This is just nonsense, first because of the fact that this is very imprecise, right? It's no way to say what exactly is a measurement, or what exactly qualifies as an observation, right? There's no measurement is in the end also nothing else than a certain sense of, than a certain physical interaction between systems, right? There's no way to, it's not a primitive category measurement in and by itself, right, that would be distinct from other sorts of physical interactions. So there's no sharp way to say what qualifies as a measurement or what qualifies as an observation. Second of all, as we have said, a measurement device or even an observer, okay, is in the end also a physical system that must be in principle describable by quantum mechanics. So this collapse postulate works for all practical purposes, right? It works, and for all practical purposes, in some sense, there's something right about it, right? Because it describes in the end what we see, and it gives the right probabilities, but this is not something that you should accept in a precise physical theory, okay? You should demand more of your theory than such a vague collapse postulate, which is just ad hoc and imprecise. And don't take my word for it. Here's a very nice quote by John Bell from his famous article against measurement. He said, "It would seem that the theory," he means orthodox quantum mechanics, "is exclusively concerned about results of measurement and has nothing to say about anything else. What exactly qualifies some physical system to play the role of measurer? Was the wave function of the world waiting to jump means collapse, for thousands of millions of years until single-celled living creature appeared, or did it have to wait a little longer for some better qualified system with a PhD? If the theory is to apply to anything but highly idealized laboratory operations, are we not obliged to admit that more or less measurement-like processes are going on more or less all the time, more or less everywhere? Do we not have jumping then all the time? Okay, so let's forget about the collapse postulate. Let's demand a solution which is more precise, more rigorous, and let's look at what our options are. We said we have here three polar positions that are just logically inconsistent. First, the wave function is complete, a complete description of the system. Second, the wave function evolves according to a linear wave equation, so a unitary time evolution. And third, measurements usually have determinate results. These propositions or statements are logically inconsistent, and they constitute the measurement problem. So if you want to solve the measurement problem, we have to give up at least one of these three principles. So if we give up the first principle, then the wave function is not the complete description of the physical system. Then we have to look for additional variables that give us a complete description of the physical system. That is, we have to look for additional variables that do make the difference between a dead cat and an alive cat, or the difference between a pointer pointing to the left and a pointer pointing to the right. Unfortunately, we do not have to look very far, because the choice, or there is a very natural and obvious choice of additional variables that you can add to the quantum mechanical description, okay? Which is just the actual configuration of the system, meaning the actual particle positions making up a system, a microscopic system or a macroscopic system, okay, that determine the actual state of the system. That is, if we say that the pointer is pointing to the left, okay, mean what you say. Mean that the pointer is a configuration of matter made out of particles, and these particles are in a configuration, right, that make up a pointer pointing to the left. Or they are in a configuration that make up a pointer pointing to the right. And it's not obvious that such a description is possible, but we will talk a lot about that, and we will see that such a description is indeed possible. So if we give up the idea that the wave function is a complete description of the system, we have to give a complete description of the system, and the simplest and most natural way to give a complete description of the system is to add particle positions. Take seriously the idea that matter is made out of particles, right? And these particles are characterized not only by their quantum state, but they have a determinate position in space, a position that changes according to a law of motion, right? And the complete description of a physical system then is given by the quantum state, the wave function, and the configuration of the system as described by the positions in space of its constituting particles. And this solution, this description leads to a theory which is known as Bohemian mechanics, or the de Broglie-Bohm theory. And we will talk about that. We will honestly mainly talk about that, because this is, in my opinion, the most convincing solution to the measurement problem, and it's also the one that I'm most familiar with. But there are other possible solutions to the measurement problem. In any case, in Bohemian mechanics, the idea is that the complete state of an n-particle system is described by a pair, psi q, where q describes the actual configuration of particles. And here is one observation that is important, but may sound a bit, no, this is not it. So the particle configuration moves according to a law of motion that is described by the wave function. We will talk about this law of motion and how it goes together with quantum statistics and how quantum probability comes out of that. And the observation that I wanted to make is that particles are the ontology of Bohemian mechanics. Okay, so this is not supposed to sound too philosophical, although this is nowadays a philosophical term. Ontology means what is there. okay? It comes from the Greek words, I think ontos, which means like to be or being, and logos, which is the theory or yeah, a description word. So this is basically the theory of what is there. And ontology is just a commitment that the physical theory makes about what there is in the world. Okay, we want a physical theory, a fundamental physical theory, to describe the physical world, to describe the world we observe. And one important step towards such a description is to make a commitment about ontology, a commitment to what is fundamentally there in the world. And the Bohemian commitment is to particles. Bohemian mechanics is a theory about particles in space or space-time that move according to a law of motion. And according to Bohemian mechanics, this table is made out of particles, this blackboard is made out of particles, and a pointer pointing to the left is made out of particles, and a dead cat and then a live cat are made out of particles. So this is the ontology of the theory, what the theory is about, what the theory postulates as the fundamental physical objects that it wants to describe. Yes? Yes. Sorry, can you speak up? Yes. That we? Yes. So in some sense, it depends what you mean by hidden variables. So yes, this is a common terminology in quantum theory that you say if the wave function has the complete description, you add so-called hidden variables. Okay? There are many reasons why I think this is not a good terminology. First off, it is misleading to say that the Bohemian positions are the hidden variables, because according to the theory, if you believe Bohemian mechanics, if you take Bohemian mechanics seriously, then the Bohemian positions are not hidden at all. It is what you actually see. So you see the table here because the Bohemian particles that make up the table are actually here. So the Bohemian positions, there's a very limited sense in which you can measure individual trajectories. But in the end, if you see a macroscopic object like a table here, or a pointer of a measurement apparatus pointing to the left, and this is because the Bohemian particles making up the systems are actually where you see them. So they are not hidden. Second, the hidden variables project historically in quantum mechanics was basically to ask, you have this quantum observables, right? This operators, and they gives you statistics for certain observables, right? Could it be that, and they seem to be random, the outcomes seem to be random, right, of such a measurement. If you measure spin, for instance, or if you measure energy or angular momentum or whatever, any quantum observable. And the hidden variables program was, so to speak, or it wasn't really a program, it was more of a question. Could it be that underlying, right, behind these quantum observables are really determinate states that predetermine the outcome of such a measurement, in the sense that if you measure that a particle has spin up, right, then there is really an intrinsic property of the particle that you are measuring, which is his spin, and that determines the outcome of this measurement. And if you measure spin down, you measure another predetermined property of the particle, which is just there. And the question was whether behind these quantum observables there are these underlying hidden variables. And it turns out that this is not possible. At least there are very strong restrictions on that. You have these various no-go theorems for hidden variables, like the Kochen-Specker theorem, for instance, which says that under relatively general assumptions, this is impossible. And Bohemian mechanics is not doing that, so to speak. We will talk about that, but Bohemian mechanics explains why a quantum measurement of some observable usually does not measure a predetermined property of the particle. So Bohemian mechanics is not trying to do that, to say that behind these quantum observables there are some hidden variables that are somehow predetermined properties of the particles that are just being revealed in experiments. Bohemian mechanics is not doing that, and if it would do that or try to do that, then it would be wrong, right? Because we have these no-go theorems for hidden variables, which shows that this is not possible. Yes? Sorry, behind you was first. Yes. Does it play any role? It plays a role in the sense that the uncertainty principle, just in quantum mechanics, is a theorem of Bohemian mechanics. So you can derive the uncertainty principle, but you have to read correctly what the uncertainty principle is. The uncertainty principle gives you a lower bound, right, on the statistical variance of measurements of position and momentum, right? But it is a fallacy to say that because you cannot measure with arbitrary precision position and momentum at the same time, that this implies that the particle cannot have a position and a velocity which is determinate at the same time, right? So according to the so it is often said that the uncertainty principle tells us that a particle cannot have a definite position and a definite velocity or momentum, right, simultaneously. But note, this is also a statement about ontology, a statement of about what is there. So the statement is, uncertainty principle says a particle cannot have a determinate position and velocity at the same time. And this is wrong. And Bohemian mechanics, as you will see, is a counterexample to that. What the uncertainty principle says, and this holds also in quantum mechanics, is there are certain restrictions to how accurately you can measure these quantities, at least in a statistical sense, right? But this is a statement about epistemology, so to speak, about what you can know or about what you can observe, not a statement about what there is, right? So in Bohemian mechanics, so the velocity of the Bohemian particles is not the momentum that you usually measure. This is also something that you can, so usually if you do a momentum measurement, you do not measure the Bohemian velocity. And for the momentum and position measurements, for the statistics of them, you have the uncertainty principle coming out as a theorem in Bohemian mechanics, as it does in standard quantum mechanics. But this does not mean that one individual particle cannot have a determinate position and a determinate velocity at any time. Yes? Sorry? Why? Yes. Because, so the simple, one answer is that the psi determines the law of motion for the particle. The configuration of the system is described by Q, but basically the configuration of a system is not enough. You also want to know how the system moves, how the system evolves. And to know how the system moves or evolves, you need the wave function, because the wave function determines, the precise law will come later on a later slide, but here this upper index psi is supposed to indicate that this velocity law is, the wave function is determined by the wave function. So the wave function determines the law of motion. And then for the Bohemian particles, and then if you analyze this theory, you will also see that this wave function also describes the statistics of a Bohemian system, as it usually does in quantum mechanics. But this is something that we will have to talk about and to see how exactly this comes out. But so basically, Q describes the position of the configuration, the spatial configuration of the system, and psi describes the state, the dynamical state, if you want, of the system, how the system moves or evolves. And so historically, there's also not such a lucky terminology, I think, but this theory was sometimes also called the pilot wave theory, because the idea was that the motion of the particles is guided by the wave function, right? And so this is a pilot wave for the particles. And yeah, this is in some sense correct, only if you have a many particle system, you will have to think in configuration space, right? A many particle wave function is not a wave in physical space. So this is a bit, picture can be a bit misleading if you think about a physical wave and a particle basically surfing on this wave. This is too naive. But basically, the wave function in configuration space determines the evolution of the particle configuration. Yes. Yes. Mm-hmm. Yes. Nothing. It's just what you say. So you can so you cannot measure these quantities simultaneously at the same time, and it's easy to understand why you cannot do that. Because to measure something, let's say the position, you have somehow to interact with the system, and if you interact with the system, you change its wave function in some sense, right? This is what the interaction does, and by changing the wave function, the velocity changes. So it's easy to see that by analyzing. So the precise formulation of the uncertainty principle you get out of a statistical analysis. But it's easy to see that first off, the Bohemian position is not an observable in the usual sense. So usual quantum measurement, if you measure position, if you do a momentum measurement, it will not measure in general the Bohemian velocity. And second of all, it's easy to see just by analyzing the theory that you cannot measure position and velocity to arbitrary accuracy at the same time. But again, don't confuse a statement about epistemology, a statement about what we can know or measure, with a statement about ontology. Also, I think you've seen yesterday that there's a sense in which you can do a weak measurement of Bohemian velocities. And there are some debates about that, in which, about the status of such a weak measurement, if you should recognize it as a faithful measurement or not. But, right, in quantum mechanics, it's a very important development with these weak measurements and so on, that our notion, our understanding of measurement somehow, what a measurement means somehow becomes wider. And if you include weak measurements, then can actually measure the Bohemian trajectories or the Bohemian velocity field at least. Sorry, that was here first, yes. Yes. Isn't this a special choice? Yes, yes and no. So first off, there are like technical reasons, I think, why you cannot write down a Bohemian mechanics for momentum, let's say. But this is a question that I often get from physicists, like, why choose Q? Why choose the position of the variable as the additional variable, so to speak? And this is so if you think from a very technical point of view, so there are all these quantum observables, right? And you pick one of them, position, then it may seem random. But in the end, you want a theory that describes the world, that describes the world that we live in and the world we observe. And in the end, we do live in physical space, right? It is not clear how a description in terms of momentum or in terms of energy states or whatever would describe our actual world, the world that we live in. In the end, you want something that describes tables and chairs and blackboards. And the best way to describe them is in terms of their configurations. They are configurations of matter in physical space. Well,
yeah, it depends what you want to do. Yes, there are mathematical. So I don't know. I think Bohm looked at theory. Bohm himself, I think, looked at the theory with momentum, and there is some reason why it didn't work, but I cannot tell you exactly what goes wrong. But no, that's a very important point that we will also discuss in detail. It's explicitly non-local. And if it were local, it would be wrong because of Bell's theorem. So we come to that. But again, take this notion of, so I don't know, I cannot tell you exactly what goes wrong if you want to add other variables. But take this notion of ontology seriously. Take seriously that you want a physical theory that describes, that tells you what is actually there in the world. Okay? And then this is the natural choice to talk about stuff in the world, about matter, described by its configuration in space and time. This is what the theory wants to describe. There are also other projects along this line, along these lines, adding other variables to the wave function. I don't know, Leggett had, I think, proposals with some sort of spin. Those were really hidden variables, and I think they were ruled out experimentally and so on. So just as far as the logical structure of the measurement problem goes, logically it's possible to explore other possibilities. But this Bohmian approach to talk about particle positions and particle configuration is the most successful one so far, and I would say also the most natural one. If I have time, a bit, yes. Mm-hmm. Yes. 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 Yes, right. Well, it's a precise and well-defined theory, and textbook quantum mechanics is not. Well, there's some sense in which standard quantum mechanics, in the sense that, so Bohmian mechanics is a theory that actually speaks about stuff out there in the world. So the world could really be, so we know that Bohmian mechanics, at least in this non-relativistic sense, is not the final theory, that it's valid only in some limited regime, but at least in this limited regime, it could be true. So it could, the nature could actually be as Bohmian mechanics describes it to be. I don't know even what it means to say that nature is as textbook quantum mechanics describes it to be, because textbook quantum mechanics doesn't even try to give you a coherent picture of the world, so to speak. So in terms of an effective formalism, right, a measurement formalism, measurement algorithm to compute statistics of experiments, standard quantum mechanics is completely fine. But Bohmian mechanics basically grounds the statistical formalism. So Bohmian mechanics is a way to say what is the fundamental microscopic theory that actually gives rise to the statistical formulation, which is textbook quantum mechanics. Right now, you mean, yes, there's a classical limit in Bohmian mechanics, but classical limit is always difficult mathematically. But in Bohmian mechanics, it's clear what the classical limit is. You can prove or try to prove that in certain situations, the Bohmian particles move to good approximation on classical trajectories. This is the classical limit in Bohmian mechanics. In standard quantum mechanics, I'm not even sure what the classical limit means. I mean, classical limit of what? If you don't have particles, what? what do you get? How do particles all of a sudden arise in a classical limit? I mean, you can do Ehrenfest theorem or something like that and then see that expectation values of certain systems evolve approximately Newtonian, but it's not exactly clear to me what it means. But the statement that I would make is that the standard quantum formalism, the standard quantum textbook formalism, arises from a statistical analysis of Bohemian mechanics. So it is something like the statistical mechanics of Bohemian mechanics. And the Bohemian mechanics is the fundamental, the microscopic theory that gives rise to this formalism. So I personally wouldn't put the problem standard quantum mechanics versus Bohemian mechanics, because I don't think that this is even an equal comparison. I would say that to the degree that standard quantum mechanics, the measurement formalism, is true, is correct, and there are good reasons to believe that Bohemian mechanics is correct and gives rise to this measurement formalism. But in the end, you know, we always, if we want to choose between different theories, we always have to, I mean, experiment is the most important arbiter, but there are other considerations as well, right? Like consistency, beauty, simplicity that we have to take into account. So different people may come to different conclusions about which description of the world compatible with the experiment feels most compelling to them. Yeah. Yes, I would agree with that, yes, but I mean, there's still the many worlds theory, which I think is a logical possibility. So, yes. Yes, right. Yes. But, well, the question was exactly, so many was that collapse models do make predictions, at least in principle, that deviate from standard quantum mechanics, and Bohemian mechanics doesn't. This is correct. So, yeah, I think okay. That's a good question. We will discuss that in detail, I hope, if we have time. So in principle, yes, but there are some costs to that. Sorry, could you speak up, please? No, there's a relatively strong sense. There's a relatively strong sense in which Bohemian mechanics and the predictions of and standard quantum mechanics, to the degree to which standard quantum mechanics is well defined, are empirically equivalent. So it's hard to, so if these assumptions are correct in Bohemian mechanics, then it won't be possible to give an experiment which would convince someone that Bohemian mechanics is correct rather than textbook quantum mechanics, to the degree that textbook quantum mechanics makes sense. I can show you, or I think you've seen yesterday, for instance, the weak measurements of the photon trajectories, right? And I can show it to you and say, look, these are the Bohemian trajectories, and Bohemian mechanics predicts that these are the trajectories. And now you see them, and now this is a confirmation of Bohemian mechanics. But of course, many people, or most people, would not accept that, because they can get the results of this weak measurement just from the standard operator formalism of quantum mechanics. So in the end, as I said, there are always, you always have to take into consideration also weak criteria. So the arguments for Bohemian mechanics is that it is empirically equivalent, so it reproduces the very well confirmed predictions of quantum mechanics, and it is a simple, elegant, well-defined theory that gives you a coherent picture of nature, and that actually explains to you where all these things come from. They explain to you why these operators are relevant in quantum mechanics. They explain to you where these quantum probabilities come from. They explain to you where non-locality comes from, and so on and so forth. Yes. Yes and no. So again, in quantum field theory, there's the same problem that it's not clear what the theory even talks about. It's not clear what the ontology of the field theory is. There are Bohemian extensions to field theory, or so-called bell-type field theories, that do have an ontology. So they are trying to, right. So those theories you can take more seriously as a true description of the world. But in quantum field theory, you have other issues, such as self-interaction problem, UV divergences, and so on, that Bohemian mechanics doesn't solve. Yeah. In principle, it's possible to extend Bohemian mechanics to quantum field theory, and there are different proposals for that. Yeah, so in the simplest case, you would have to add a law, a statistical law, how particles are created and annihilated. So you take seriously the state on Fock space with a variable particle number, and you add a law, a stochastic law, that gives you Fock space jumps. So with the rate predicted by quantum mechanics, the system can jump in Fock space, meaning that particles can get created and annihilated. And in this sense, you can make a coherent Bohemian picture. But I feel like, we haven't really talked about the details of the theory, so we should postpone these more expert questions, so to speak, after we have discussed the basics of the Bohemian theory, because I didn't really show you anything except of the slide, and there are a lot more to say about that. But before we discuss Bohemian mechanics, I also want to mention the other logical possibilities, right? We have these three statements that are logically incompatible. So you can also give up the second possibility. So give up the concept that the wave function always involves according with a linear dynamical equation, the Schrodinger equation. But of course, you have to be careful in giving that up, because at least on microscopic scales, okay, the Schrodinger equation is very well confirmed. And the existence of superpositions, at least on microscopic scales, are very well confirmed, right? So the question is, how do you modify the Schrodinger equation in such a way that you basically keep the microscopic superpositions, so keep the linearity of the time evolution on small microscopic scales, but still rule out those macroscopic superpositions that would be problematic and then we don't observe. And in fact, the ingredients are already there in standard quantum mechanics, right? You have the linear Schrodinger evolution and you have the collapse of the wave function, only that this collapse of the wave function is ad hoc. It is not a precise law of nature as it's formulated, and it makes reference to vague notions such as measurement or observation that shouldn't be there in a fundamental physical theory. But there is the possibility of making this precise just by adding a precise mathematical collapse law. And the first proposals along these lines is the GRW theory, named after Girardi, Rimini, and Weber, who introduced a precise collapse law, a statistical collapse law for the wave function. And the idea is like this. between jumps, so between these collapse events, the wave function evolves just according to the usual linear Schrodinger equation. But sometimes, randomly, a collapse happens, a jump, a collapse event happens. And what the collapse does, basically, is to multiply the wave function by a Gaussian and localize it in that way. So if you have here a superposition and the collapse hits, so the collapse hits random in time, so it's basically a Poisson process, a distribution with some sort of frequency, which is lambda, which is a new law of nature. So when the collapse occurs is random, and where the collapse occurs, so where the center of the collapse is also random, but this collapse center is approximately distributed with the psi-square distribution given by the wave function, right? So for instance, if this is basically 1/2 of the weight of the wave function, then you have probability 1/2 that the collapse will occur somewhere here, and probability 1/2 that the collapse will occur somewhere there. And if the collapse center hits here, so to speak, you have here multiplication with a Gaussian, and that will suppress this term here, will become very small, and accentuate this term there, will become very, very large. And then if a second collapse hits, right, it will hit with very great probability here, right, further accentuating this part of the wave function and further suppressing this little bump of the wave function. And here you have two new constants of nature, basically. One is this collapse rate that tells you how often a collapse occurs, and one is this collapse width, which tells you how precise, basically, the collapse here, the wave function gets localized, and these are new constants of nature. And this collapse rate, so you have some wiggle room there to adjust these parameters to experiments, right? There are a lot of experiments going on to exclude some ranges of parameters, but the classical proposal for the collapse rate was, I think, once every 2 to the 15 seconds, and the estimated age of the universe is 10 to the 17 seconds. So on average, one particle would have collapsed one single time. The wave function for one particle would have collapsed one single time in the history of the universe. So basically, microscopic superpositions of small system of one particle or very few particles, they basically survive arbitrarily long, so for many, many years. But if you have a macroscopic system, right, in a macroscopic system, the number of particles is typically of the order 10 to the 24th, so typically of the order of Avogadro's constant, and there, right, you have some collapse. There you have a lot of collapses, right? So basically, you have the number of collapses per second is then 22 times 10 to the minus 15. So you still have a billion collapses per second, right? So macroscopic systems are basically collapsed. Microscopic superposition disappear basically instantaneously before you could ever observe them. No, yeah. So it's common also in these other theories to use the name of particles, but think of particles basically as degrees of freedom in the wave function. There are no particles as in the Bohemian sense, right? In the Bohemian mechanics, when you say particles, you mean something that exists in space and is localized in space. And here, by one particle, you just mean one degree of freedom in the wave function of the system. Ah, right. Ah, that's what you mean. Yes. Okay, yes. Sorry, I should have said that more precisely. So there's not only, so you have to play a bit around with these constants of nature, and so state of the art is that you have to make these the collapse rate mass dependent. To be empirically adequate, you have to make the collapse rate mass dependent. And I guess, yes, there would be about the collapse rate of a nucleus then. So let's talk also about the third possibility, right? The third possibility is deny that the measurement usually has a definite outcome. That means basically keep just the wave function and the Schrodinger time evolution and by these consequences. Okay, so by the consequence that in the end you really have a pointer pointing to the left and a pointer pointing to the right. And try to reconcile this picture in which you have only the wave function and the linear time evolution with our empirical evidence and our empirical observation. And this is, in fact, an important point, an important observation, which is usually attributed to Hugh Everett III, which is often credited basically as the founder of the many worlds interpretation, although it is historically not clear if he ever really had a many worlds picture in mind. What is clear, what he had in mind, is that this Heisenberg split, splitting the description into a microscopic quantum description and a macroscopic classical description cannot work, right? It was clear to him that if you want to take quantum mechanics seriously, then you have to take quantum mechanics seriously on all scales. And ultimately, the only wave function that you have is the universal wave function, the wave function of the universe as a whole. In any case, what he observed is that if you take quantum mechanics seriously and take it seriously on all scales, then the superposition doesn't stop with the pointer or doesn't stop with the cat, right? The experimentalist and his laboratory, and indeed the whole environment, the whole world, they are also described quantum mechanically, and they also take part in this superposition. So if we go at least one step further, okay, and add, so to speak, the quantum state of the experimentalist, right? In one scenario, you will have an experimentalist that sees an alive cat and takes the cat home and pets it and gives it a glass of milk, or bowl of milk. And in the other case, you will have a sad experimentalist that sees that the cat is dead and that goes to make a funeral for the cat, and that is maybe sued by animal protection or whatever. So it goes on and on. And in the end, it includes the entire world. In the last resort, the entire universe, right? It gets entangled with this microscopic history. And due to linearity, okay, if you start with a superposition, you end up with this microscopic superposition, which is, in the last resort, okay, a branching universe, right? One universe, one world, so to speak, in which we have an alive cat and a happy experimentalist, and one world in which we have a dead cat and a sad experimentalist, right? And I think the important observation of Everett and of the many worlds theory is thus that you cannot, right, contrast to first appearances, you cannot straightforwardly rule out this macroscopic superposition on a purely empirical basis, right? So, of course, we said, and yeah, this is very suggestive, that we said this macroscopic superposition, or I said it, not we said it, I said it at least, that this macroscopic superposition is obviously something that we do not observe. And in some sense, this is correct. But if we take this picture, this pure wave mechanics, to its logical conclusions, okay, then we should not expect to observe it, right? I should not expect to observe in one world a pointer that points simultaneously to the left and to the right, but I should expect that with the superposition, if I do such a quantum experiment, right, I exist twice, right? I exist in one branch of the universal wave function, and I see the pointer pointing to the left, and I also exist in another branch of the wave function, right? And in which I see a pointer pointing to the right. Okay, so in some sense it's correct that I do see a pointer pointing to the left and a pointer pointing to the right. The question is what I mean by I. So in this picture, I would exist at least twice after this quantum experiment in two different branches of the universe. And these branches of the universe, they are decoherent, right? They do not overlap with each other because the wave function of a dead cat and a happy and a sad experimentalist and the wave function of a live cat and a happy experimentalist, they are macroscopically disjoint on configuration space. They are concentrated on different parts of configuration space and do not overlap with each other. And this means that these different branches of the wave function, these different worlds, are causally disjoint. They do not interact with each other. So if I see the alive cat in my box, I would have no way to make contact with the physical interaction with the other branch of the wave function, in which I see, in which there's another copy of myself that sees the alive cat. And this is obviously, this many worlds picture is an extremely bizarre picture, I would say. I think intuitively most people would agree, but at least logically it is a possibility that one can take into account, and we can see how far it goes. And many people actually take it very seriously. So many people think that quantum mechanics is a many worlds theory. And this is what we learn from quantum mechanics if we take the equation seriously. And in fact, I don't like the word interpretation of quantum of a theory, but to the many worlds interpretation, it is somewhat applicable. And then the many worlds interpretation is not one interpretation of quantum mechanics. I would say that in some sense it's the only interpretation of quantum mechanics. Namely in that sense that if you take seriously that there's only the wave function and only the linear Schrodinger evolution, then you end up, if you take it to the logical conclusion, with such a many worlds picture. Yes? Yes. So these worlds, so to speak, they are emergent. And they are emergent through decoherence, right? So, and decoherence happens, first it happens gradually, and it happens just when, larger parts of the environment are involved. So in one world, right, a microscopic superposition does not lead to a branching of the universal wave function. So you can have in one branch of a universal wave function, you can have a coherent superposition of a particle going to one slit or a wave going to one slit and going through the other slit. But as this interacts with a macroscopic environment, then you get coherence, and at some point this decoherence is so far that you end up with a branching universe with different branches of the universal wave function that are causally disjoint. But in one world, you can still have coherent superpositions if you, as long as you can keep out the coherence, so to speak. Yeah. Yeah, we will talk. So I would disagree, but I would think that Bohemian mechanics does give a very good explanation of the Born rule, and I think that, I think the collapse models, I would also say, I think yeah, okay, yes, yeah, that's a good point. That's a good point. But if you accept the law as it is, it's rather straightforward how the Born probabilities come out of it. And in Bohemian mechanics, there's a more sophisticated argument involved that we will hopefully talk about either today or tomorrow. But I think the greatest issue is in many worlds theory. Here, actually say, one challenge is how to explain the quantum probabilities, right? If all possible measurement outcomes occur. So in the many worlds theory says that if you do a spin measurement, let's say, then the system is not, the measured system is not in an eigenstate, okay? Then the measurement result is always spin up and spin down. Or in general, in every quantum measurement, all possible measurement outcomes are realized in one branch of the wave function, one world. So it's not clear even what it means that a certain measurement result or that a certain measurement outcome happens with a certain probability, because strictly speaking, everything that is possible happens with probability 1, just in one branch of the wave function. So there's an issue there, right? The issue is not just how to get from a deterministic description, right? The Schrodinger equation is a deterministic equation. So the many worlds theory is a deterministic theory. But the issue is not just how to get from a deterministic theory to probabilistic predictions. That issue you also have in Bohemian mechanics, and we will discuss how this works. The issue in the many worlds theory is deeper, namely, what do you even mean by probabilities? There doesn't seem to be any interesting frequencies, so to speak, because everything that is possible happens. But there is a lot of literature about that. Everett, I think, has given, actually, I think Everett has given the best answer to that to date, although the many worlds community does not really accept Everett's answer, and they try to do other derivations of the Born rule as a subjective probability, using, for instance, argument from decision theory. So they want to set up rationality principles that tell you that if you live in a many worlds universe, you should basically bet on outcomes as if the Born rule was true, and so on and so forth. But there's a long discussion about how accurate this is. Can I take the question, or should we stop? Okay. Yes. Well, so if I understand you correctly, this is what most people would do or would try to do, but it gives you the wrong statistics, right? So what you can do, so suppose you have, I don't know, let's suppose you do a spin measurement of a particle that is in this state. You do a spin measurement, and according to the many worlds interpretation, you have one world in which you measure spin up, and here the measurement device is in spin up, and in the other world you measure spin down, and here you have spin down. The pointer, the measurement device shows spin down. And you can do this repeatedly, right? You can here do here a second measurement in an orthogonal basis if you want, right? And so you have a splitting again here. Yes, also. Yes. So in this particular example, it's correct, right? In this particular example, you just count, and you will see that in half of the worlds you have measured spin up, and in half of the worlds you have measured spin down. And the thing is that in this very particular example, it fits with the predictions of quantum mechanics, with Born's rule. But what if you start in such a state, right? Then according to Born's rule, according to quantum probabilities, it is twice as likely to measure spin down than to measure spin up. But in this many worlds picture, if you just do what one calls branch counting, So just count the number of worlds in which you have the outcome is spin down and in which the outcome is spin up. You still get 1/2 and 1/2. In 1/2 of the worlds you have spin up, and in 1/2 of the worlds you have spin down. So this very intuitive thing to do, which is actually how many people set up the problem, leads to the wrong probabilities, because it does not in general lead to the Born probabilities. Yes. Yes. No, why? Maybe we should talk about it during the break. Maybe I misunderstand you, but if I understand you, as I understand you, you would just get 1/2, 1/2. So each measurement, right, on each system would give you one branch in which you have spin up and one branch in which you have spin down. Okay, so yeah, thank you very much. We are a bit over time, but we will go on in the next lecture this afternoon. So thanks for the participation and the question.